Welcome back to the glass plate. In one of the previous examples, we discussed the evaporation of a solid sphere, an air refresher, due to a higher concentration around the sphere and hardly any in the air far away from it. And we backed out from a mass balance that the change in diameter is given by this equation. The diameter at current time minus that initially is given by this proportionally to T. Let us see how quickly this evaporation takes place. So we're going to put in some numbers. But before we do so, let's just use our ballpark numbers understanding. If this is an air refresher that you put in your bathroom and you let it evaporate, what will your guess be? How long does it take before, for instance, if this is initially a centimeter, how long does it take before it's halved and only 5 millimeters is left? That is not so difficult to roughly, really coarsely estimate. For instance, if I would say, well, that is about half an hour, what would be your response? Well, most likely you would wonder, why do you buy it? Every half an hour you have to replace it. What kind of air refresher is that? So it must be much longer than that. On the other hand, if I would tell you, well, it's probably a little over 10 years, then you would be happy, but any company who makes these would have a hard time selling them. So it cannot be that slow either. It must be somewhere in between. So if I use my gut feeling, I would say something like months or a year, 2 years at maximum. Okay. Let us do the real estimate and put in some numbers. I already gave that it's a centimeter, and I'm going to ask at which time tau is d half a centimeter. So it's half. So I know this side of the equation. On the other side, I have two concentrations, a diffusion coefficient and the density of the material. The density of the material is on the order of that of water, slightly less for these materials, they float. So let's just put in a number, 800 kilogram per cube. Diffusion coefficients in air, is diffusion in air, are on the order of 2 × 10⁻⁵ meters square per second. So all is left is these concentrations. Well, the concentration far away is probably very, very small, so we equate that to 0. There is always some refreshing of air in your bathroom, so this doesn't go up. Concentration here close is in equilibrium, close to the surface, and we need to find that. That is usually not specified as a concentration, but for many substances that evaporate very slowly, you find it as a vapor pressure in equilibrium with the solid material. That vapor pressure can be turned into a concentration in kilogram per cube by the ideal gas law. For that, I need to write down the connection between a concentration, kilogram per cube, and the ideal gas law. Ideal gas law, pressure, volume, equals number of moles, gas constant, times the temperature. Here is where the concentration is hidden or can be backed out. Rather than writing N, I write N over V. That is the molar density. If I multiply that by the molar weight, I get the concentration I am looking for. This molar weight is again something that I can look up. Now if you look at what M times molar weight over volume is, then the ideal gas law tells you that that is P times the molar weight over RT. P is the vapor pressure, I looked that up. M is the molar mass, on the order for these substances of 100 gram per mole. R, gas constant, I know. T, room temperature. If I look it up, I get something on the order, let me take a look at my piece of paper, 3 × 10⁻⁴ kilogram per cubic meter. Pretty low. Therefore, slow diffusion is to be expected. Okay, now I can put everything together and I back out the time that I wrote here. Let me move over a little bit and write explicitly this time. It is d0 squared minus half of that, so squared gives a quarter. I use the minus sign to flip these two. I need to divide this by 8, multiply it by the density of the solid material, divide it by the driving force outside the sphere in the air, which is only c star because this is negligibly small. And then I should not forget diffusion coefficient, 1 over d. Stack in these numbers and you're going to find that this is roughly 5×10 to the power 6, so 5 million seconds. Sure, pretty long. But if we equate that to days or months, it's not that long anymore. It's a number that we can handle and understand. Roughly 2 months. Makes sense, doesn't it? You put it in your bathroom and on the order of 2 months to half a year you have to replace it. Try these yourself. Think, for instance, what happens to a cube of sugar if I put it in my cup of tea and I don't stir? Then you can repeat this analysis. Try and look up the C star of sugar in water and try and back out numbers and see whether you find reasonable times for dissolving sugar without stirring. See you in the next lecture.